How do you choose boundary conditions for stress simulations? Imagine trying to figure out how a bridge will hold up under heavy traffic without actually building it first. That's what stress simulations help us do. But to get accurate results, you need to set the right boundary conditions. Think of boundary conditions as the rules that tell your model how it can move or stay fixed in the real world. If you set them wrong, your simulation might give you answers that don't match reality. So, how do you pick the right ones? Let's walk through it. First, you need to understand the real physical situation. Ask yourself, how is this part supported in real life? Is it fixed to a wall or does it slide on a surface? Are forces applied at specific points or spread out over an area? Knowing these details helps you decide what constraints to apply in your model. For example, if a beam is bolted at one end, you might fix that end in your simulation. If it's free to move, then you don't want to overly restrict it. Next, it's important to prevent the model from moving in ways that aren't possible in real life. This means applying constraints to stop it from shifting or rotating in space. Usually, fixing a surface or a point is enough, but be careful not to overdo it. If you constrain too many parts, your model might become too stiff, and the stress results won't be accurate. It's a balancing act. Another key point is to model supports realistically. Instead of assuming they are perfectly rigid, consider supports that have some flexibility. For example, using spring elements can better mimic real supports that can deform slightly under load. This approach helps you see how stresses distribute more accurately. When applying loads, make sure you choose the right type. Point loads, distributed pressures, thermal effects, or inertial forces all behave differently. Applying a force at the wrong spot or using the wrong load type can lead to errors. For example, if you're simulating a pressure on a tank wall, you need to apply it over the entire surface, not just at a single point. If your model is symmetric, use symmetry boundary conditions. This reduces the size of your model and saves computation time. For example, if a structure is symmetric along a plane, you can constrain the displacement along that plane, which automatically prevents movement in certain directions. In assemblies, contact conditions matter a lot. You might need to specify frictional contact, bonded contact, or elastic supports. These details influence how stresses transfer between parts and how they deform under load. Ignoring contact conditions can lead to overly simplified and inaccurate results. Finally, always compare your simulation results with real data or analytical calculations if you have them. If the results don't match, revisit your boundary conditions. Maybe supports are too stiff or loads are not applied correctly. Adjustments might be needed to better reflect the actual scenario. In a typical static stress analysis, you'll fix supports where the structure is attached, apply forces or pressures where loads act, and include environmental effects like gravity or temperature if relevant. Using elastic supports instead of rigid ones can help if supports are flexible. Remember, the goal is to mimic the real-world behavior as closely as possible while keeping the model stable and solvable. Choosing boundary conditions is about finding the right balance. You want to accurately representing how the structure is supported and loaded without overconstraining it. When done well, your stress calculations will give you reliable data to guide your design and ensure the mechanical integrity of your project.